Alrighty, folks. Thanks for your patience. We're going to talk about chapter 2, atoms, molecules, and ions. And we're going to do a couple of review pieces. So the first thing that we're going to review is talking about this unit, parts per million. So 1 part per million is like 1 inch in 16 miles, or 1 second in 11.5 days, or 1 minute in 2 years, or 1 car in bumper-to-bumper traffic from Cleveland, Ohio to San Francisco, California. If visually, right, it helps you to imagine what that would look like. 1 part per million is 1 teaspoon in 1,302 gallons, or 2.3 500-gallon hot tubs. 1 part per billion then would be 1 teaspoon in 1,302,000 gallons, or 63.5 20,000 or so gallon pools. So that scale really matters, and it's helpful for us to think about that. In chemistry, when we think about parts per million, we think about 1 milligram in a kilogram, because 1 milligram in a kilogram is 1 part per million by mass. So for example, 1 liter of pure water at 4 degrees Celsius and 1 standard atmosphere of pressure weighs exactly 1 kilogram. So 1 milligram per liter would be 1 part per million. Another way to say that is that a liter of water weighs 1,000 grams, or 1 million milligrams. Therefore, 1 milligram in 1 liter is 1 milligram in 1 million milligrams, or 1 part per million. So when we think about problems, sometimes it's useful to think about units and the way that that can inform our understanding of problems. So the level of carbon dioxide in the atmosphere was 317 parts per million in 1958. It is currently 414.7 parts per million. What was the percentage change in carbon dioxide during that time period? So the unit, parts per million, right, is the unit that we're thinking about here. And this is data that was collected by the Scripps Institution of Oceanography and the NOAA Earth System Research Laboratory, and they're measuring atmospheric carbon dioxide at the Mauna Loa Observatory in Hawaii. And so this is the Earth's longest continuous record of direct measurements of atmospheric carbon dioxide. So if we're thinking about this, right, remember a percent is some value X out of 100, right? And that's going to give us some decimal value. So for example, 90 out of 100 would be 0.9. We would multiply that by 100 then to get our percent. So one way that we can solve this problem is to subtract the old, or the original value, from the new value, right? So this is our original value, this is our new value, and then we multiply by 100. That gives us 30.8%. So when we think about norms again, we've talked about creating a safe space. It's really important that we recognize that questions are always welcome. There is no such thing as a stupid question. It's really important for you to ask questions, because that's how you're going to foster and develop your learning. Being able to rely on others or collaborate is critical. And then your ability to iterate or take a risk and try again is also something that we really support. So in terms of our scientist spotlights, I wanted to highlight Wallace Smith Brooker. He's a PhD. He was someone who was dyslexic. And so that meant that early on in his education, he was really challenged in terms of learning how to read, but he persisted in solving problems. He was a geochemist at Columbia University's Lamont Doherty Earth Observatory, and he predicted an imminent rise in the Earth's temperature due to human output of carbon dioxide. So you could say that he discovered global warming in the 1970s, and that he also reported out about global ocean conveyors. I wanted to showcase him as a scientist because I feel like early on he developed a persistence when it came to solving problems. And intriguingly, had he not been dyslexic, I don't know that he would have developed that persistence or that stick-to-itiveness. And that was really what allowed him to be successful in solving some of the problems. So he's a great example for us of refusing to give up and always iterating to improve our learning. So today we're going to think about naming molecules, ionic compounds, and acids. And we're going to correctly write correct formulas for ionic compounds, molecules, and acids. So it's important that we both know how to write the formula and that the actual math of the formula is correct. So those two corrects are actually necessary. Because we are scientists who do science, today we're going to be asking questions and defining problems. We're also going to be analyzing and interpreting data. And we're going to be constructing explanations and designing solutions. And then last but not least, we're going to engage in argument from evidence. So really important here when we're thinking about naming, there is an older naming system. These are what we refer to as common names from our older naming system. But the systematic name that we're going to be using is something called the stock system. This idea of a naming system is what we refer to as nomenclature. It's a set of rules that we use for forming the names or terms in a particular field of arts or sciences. When we think about IUPAC, this is actually the agency that comes up with the rules for our nomenclature, but they do some really interesting things too. So for example, they track emerging technologies in chemistry. They actually have a really cool tool for designing our climate, which is an active or proactive response to climate change. So a great resource. So in terms of our notes, right, we're thinking about how we develop a method for recording information from reading and lectures in a personally useful way. So the first piece of information that you want to find in your notes is this working definition of anions and cations. So an anion is a negative ion, cation is a positive ion. Note that when we're thinking about, right, the information we can pull from the periodic table, probably the compound that we're most familiar with would be something like a binary ionic compound. So NaCl is a great example. And from our periodic table, we can see the molar mass of sodium as well as the molar mass of chloride. These are two atoms from different elements. One atom is a metal and the other atom is a nonmetal. So in this case, chloride is my nonmetal, sodium is my metal. It's important for us to recognize that most cations and anions can combine to form neutral compounds. So typically they're solids under normal conditions that are usually referred to as salts. This idea of the net charge of an ionic compound then being zero is how we do the accounting or the math to make sense of the ionic compounds that we're forming. So therefore, the number of cations and anions in an ionic compound must be balanced to make an electrically neutral molecule. So here's an example of that. So aluminum metal has a charge of +3, and fluorine, which becomes fluoride because it gains an electron to become an anion, has a -1 charge. And so if I think about this, in order to cancel out my +3 of my aluminum, I actually need 3 of my fluoride ions so that my +3 is canceled by a -3. And that's how I get a net neutral compound, aluminum fluoride. So if you're wondering, well, where do I find these compounds? On your periodic table, everything to the left of these steps, we consider metals. Everything to the right of these steps we consider nonmetals. It's going to be really helpful for us as we go forward. So here are some examples for you to practice. So sodium fluoride, magnesium oxide, aluminum fluoride, potassium sulfide, calcium phosphide, and aluminum oxide. So think about the charge on each of these ions and whether or not they balance. That's going to be super useful as we go forward. So think about that practice. Choose one or two and practice writing out their charges and showing that electronically that balances to neutral. So when we're naming ionic compounds, the cation always retains the same name as the element, but the anion's name is similar to the elemental name, but we replace the ending of the name with IDE or IDE. So if a metallic element has cations of different charges, which cation is used has to be indicated by its suffix, which is the older method, or by Roman numerals in parentheses after its name in writing. This is what we refer to as the stock system. So again, if we think about these examples, right, all of these are examples of ions that have only a single possible charge for the metal, right? So we should be able to write these out and justify, say, for example, that sodium is a +1 charge, fluoride is a -1 charge, so the net compound is neutral. In the nomenclature of simple molecular compounds, the more electropositive atom is written first, and the more electronegative element is written last with an IDE suffix. And then we use Greek prefixes to indicate the number of a given element present in a molecular compound. So these prefixes can be shortened when the ending vowel of the prefix conflicts with the starting vowel. So common exceptions exist for naming molecular compounds. So there are sometimes trivial or common names that are used instead of the systematic names. So for example, ammonia is very common to refer to NH3 instead of nitrogen trihydride, or water instead of dihydrogen monoxide. When we remove the ending of the second element and we add IDE, just like ionic compounds, when we're naming molecular compounds, we use these prefixes. So mono indicates 1, di indicates 2, tri indicates 3, tetra equals 4, penta is 5, hexa is 6, hepta is 7, octo is 8, nona is 9, and deca is 10. If there is only one of the first element, you can drop the prefix. So for example, CO is carbon monoxide, not monocarbon monoxide. Some of these are rules that we just actually have to practice in order to get familiar with. So here's a great example of some molecular compounds that you can practice creating the name or formula for. So what does dinitrogen trioxide look like? What does diphosphorus trioxide look like? Carbon tetraiodide, sulfur dichloride, and chlorine gas. Go ahead and take a moment and practice those. You can check your answers here. So if you came up with these as your answer, then those are the correct formulas. If there are two vowels in a row that sound the same once the prefix is added, or they conflict, then the extra vowel on the end of the prefix gets removed. So for example, one oxygen would be monoxide, but instead it's monoxide, the extra O is dropped. And generally, the more electropositive atom is written first, followed by the more electronegative atom with an appropriate suffix. So for example, H2O or water can be called dihydrogen monoxide, although it's not usually. So organic molecules, molecules made of carbons and hydrogens, along with other elements, do not follow this rule. You're going to learn about naming organic molecules in Chem 111. That's outside the scope of Chem 110. So here is my recommendation. This is an example of a flowchart or a decision tree for how to name compounds. I highly recommend that you create your own. Use colors, use symbols, use boxes, use arrows. Create your own flowchart or decision tree for naming. You're going to use this on Wednesday's quiz, so it's to your benefit to take time to make sense of that flowchart. So we're going to continue our practice of arguing from the evidence. And so we're going to practice making claim, evidence, reasoning statements. And so remember, the claim is your answer. That's your statement that's going to answer a question. Your evidence is the data that you collect, either through observations or measurements. Sometimes it's your calculation. And then your reasoning is your evidence of why, right? What supports your claim? So here's an example. We're going to pick one of these, and we're going to provide the name of the compound and then provide a claim, evidence, reasoning statement. So my claim is that the name of the compound Cl2O7 is dichlorine heptoxide. My evidence is that it's a molecular compound. It's made of two nonmetals. So the two nonmetals are Cl and O. There are 2 dichlorines and 7 hept oxygens. So heptoxide. Note, right? There sometimes can be more than one piece of evidence or sometimes more than one reasoning. And that's okay, right? That's part of building the structure of how you support your claim. So if you have more than one piece of evidence or more than one piece of reasoning, that's totally okay. Reminder that Science Student Success is 11:30 to noon on Mondays and Wednesdays after class. There are also other sessions if those times don't work for you. And then we'll see you in Chem 110 discussion on Thursdays in the library. And don't forget the last 5 minutes of class. It's really important to build this practice of organizing your goals as well as your metacognition. That's your thinking about your thinking and reflecting on your learning. So goals are, right? What are short-term achievable goals about what we want to learn? And then we start thinking about the strategies that help us reach those goals. That's how we achieve progress. Our thinking is, how do you know what you know? Did I really get an idea? Could I explain it to a friend? Do I need more information or knowledge, or do I need more practice? You are the best authority to answer that question in terms of where you're at in your own learning. Part of that process is reflecting on your learning. So what were things that made sense? Congratulate yourself if you've got a concept down and you've integrated it into your framework or your schema or the way that you think and organize knowledge. What might be something, though, that needs refining or reframing? What are you curious about? Who do you learn well with? What might be your next steps? By Tuesday, we're going to make sure that we've read chapter 3, that we're working on our ALEKS, and then that our reading quiz for week 3, lecture 2 is ready to go. Thanks again.